So basically, we started discussing the timer module or timer function that is available in the HCS12 microcontroller. Okay, so we had a very, we started looking at this module, which is the TIM module. We said basically this module, if we look at the block diagram, it has at its core, there is the 16, it's not, there is the 16-bit counter, which is basically connected to the bus clock. And in this case, it is this counter is acting as a timer. It is basically counting the periods of the incoming bus clock, so it can be used. It is used as a timer. Now, this timer, it is called the free-running timer. It is a 16-bit timer, so it is running from 0 up to 2 to the power 16 minus 1. When it overflows back to 0, this event can be used to interrupt the microcontroller, and this event can be used to perform different timing operations, whether it is just measuring time or it is what we are going to discuss today, the associated or the additional timing features that come in this module, which are the input capture and the output capture operations. So this is basically what we talked about last time. We started talking about the free-running timer or counter. We said this is basically a timer that can be accessed in terms of count value by going to this register, which is the TCNT count. It is triggered by the E clock. So the time base is basically the E clock. It can be prescaled, the E clock, to achieve higher or larger time measurement. It is the base time for the other timing features, the input capture and output compare, and it can be controlled using these registers, the control register number 1, control register number 2, and the flag register number 2. Technically, in these control registers, as we saw last time, we can specify, we can enable, we can turn on or turn off the timer. We can specify what happens to this timer when the microcontroller enters the wait mode and the freeze mode, and we can enable the fast flag clear feature, which will we discuss today. Also, the second control register, we can enable the timer overflow interrupt feature. We can specify the prescaler for the incoming clock, and this is important because we need sometimes to increase the time that we are working with, the maximum time. We wrote the equation last time. The maximum time that can be measured, which is basically 2 to the power 16 multiplied by the E period multiplied by the prescaler. And finally, the overflow flag. We said that this flag is set when the timer overflows, when it goes from 2 to the power 16 minus 1 back to 0. And this flag can be, or this event can be configured to interrupt the microcontroller. So we reached at this point, we were where we have an example on using this timer. Basically, what is required here is to write a program that configures and uses the free timer or the TCNT timer to generate a square waveform, a periodic waveform on pin 0 from port B, pin 0 from port B. The frequency of this waveform is 50 Hertz, and assume the main frequency or the oscillator frequency to be 20 megahertz. So basically here we want to generate a periodic square wave on port B, pin number 0. We want to generate continuously a periodic square wave with a frequency of 50 Hertz. The frequency is 50 Hertz. In other words, the period is 1 over 50, which is 0.02, which is 20 millisecond. So the period of The board is stuck. Okay, it's not showing. Let me start the board. Okay, so the period of the signal to be produced on pin B from port 0 is 20 milliseconds, assuming 50% duty cycle, which means that the on time and the off time are equal. We have here 10 millisecond and 10 millisecond. Okay, then we basically want to generate such a signal. Now, if we don't want to use the counter, we can basically use software generated time delays. So basically we output 0 on this pin, we delay for 10 milliseconds, then we output 1 on this pin and we delay for 10 milliseconds, and so on. We keep doing that. But now we don't want to use software generated time delays. We want to use the timer, the hardware timer that is available in the TIM module. So how to do that? Basically, we need to configure the timer such that it overflows after 10 milliseconds. So when it overflows, we basically change the state of this pin. Let's say, for example, we start with 0, then after 10 milliseconds, we toggle or we complement, and we keep doing that. So basically, we need the timer to overflow every 10 milliseconds. So we need to figure out what configurations should be done to this timer. So 10 milliseconds, which is 10 to the times 10 to the minus 3, is basically 10 to the power 16, which is the maximum number of increments for this timer, times the E clock. Now, if the oscillator frequency is 10 megahertz, then the E clock is basically 5, or it is 20, yes, it is 20 megahertz. This is the oscillator, F oscillator. Then the E clock is basically 10 megahertz. So if we do the math, this will be 1 over 10 times 10 to the power 6. What is left, basically, we want to achieve this. So these are fixed. The number of increments, the frequency or the period or the cycle time is fixed. What is left is basically the prescaler. We need to figure out what is the prescaler value that will give us 10 millisecond, such that the timer will overflow after 10 milliseconds. So if we do this, this will be what? 100 times 10 to the power 3 divided by 2 to the power 16, by 2 to the power 16. So the prescaler value will be this, and usually, I think, I don't have it on the slides, but if you do the math, this will be, the P will be, I think, 1.5 something. So if you go back to the set of available values for the prescaler, you don't have 1.5. So you either take 1 or you either take the upper. So let's say we take the prescaler equals to 2. So the prescaler value should be set to 2. So if we want to use the timer also, so we figured out what value to be stored as the prescaler. We need to figure out what are the other values to be stored in the control registers. So here we have the TS timer system control register 1 and timer system control register number 2. So these are the registers associated with this timer module. So let's go back to these registers. Here, we have the control register number 1. We need to enable the timer. So at some point in our program, after we've configured the prescaler and configure the interrupt and other features of the timer, we need to come to this register and make this bit 1, and we don't care about the remaining bits, so we leave them as zeros. So at some point in our program, we need to set this register to this value. For the second control register, we are not going to use interrupts, so we'll not enable the interrupts. We will just use pulling in order to know whether the timer has overflow or not. Basically, we will pull the flag, the timer overflow flag that is in the timer flag register number 2, and these bits are zeros. And this bit, we'll leave it as is. We did not talk about it, TCRE bit. And finally, for the prescaler that we chose is basically 2. So the value to be stored in these bits are basically 0, 0, 0, 1. Hopefully I did the math correctly. And this is what we need to do with these two registers. So if we go to the program, basically it is here, it is in assembly, and next I think it is, no, there's no C version of this program. So basically we started by configuring port B as output. Here it configured all the pins for port B as output, despite the fact that we are using only pin number 0. We stored this value 0, 1 in timer in the control register number 2, so that the prescaler now is 2. Yeah, so my memory is working, so it is 2. Then we cleared the flag before we enabled the timer. Why did we clear the flag? Because I think, or I believe that if I remember, this flag, the value of this flag bit is not specified on reset. So when the microcontroller is powered up or it is reset, this flag is don't care. It could be 0 or 1. So to make sure what is the value of this flag, so we cleared the flag by writing this value. So basically we are writing 1. The T flag bit or the overflow flag bit is basically bit number 7. So we basically write 80 hexadecimal to clear the flag. So we write 1 to that flag. Then we write 80 also to the control register number 1, which enables the timer, which is the value that we figured out on the board. So at this moment, after this instruction is executed, basically the timer is enabled and it is ticking. So it is incrementing every 1/10 of 1 over E, every E period. It is incremented every E period multiplied by the pre-scaler. So in order to know whether the timer has overflown or not, we basically pull this flag, which is the TFLG2 flag, which is the timer overflow flag. This is the name of the flag, or just simply if we write bit number 7, we write 7 here, it is the same. So this is defined in the include file as a constant or an equate to imply that this is bit number 7, and this is the T flag register, the address of that register, which is also defined in the include file. If this flag is not set, then we just keep looping here. Once the flag is set, this implies that 10 milliseconds has elapsed. So we clear the flag by writing 1 to it again. We load 0, 1 XOR with port B. We store back to port B. What is the effect of this? When you XOR a value with 1, basically it complements. Or we can simply write complement port B if it is applicable. So this is how we complement the ports. And technically here, maybe we were forced to use this because we only want to complement bit number 0. So here, the mask that we are using is 0, 1. So we are only XORing bit number 0 with 1. So it will be complemented, while the remaining bits from port B are XORed with zeros. So when you XOR any value with 0, it stays the same. So this is useful in case that we only want to affect pin number 0 from port B, because other pins might be used with something else. Then we basically go back and repeat. We keep doing that over and over. Okay, so here we did not use the interrupts. We did not use the interrupts, the timer overflow interrupt. We used pulling. Is this better than using, let's say, a delay subroutine instead of working with the hardware timer? Which is better, this approach to generate this square wave with this frequency, or basically to write a subroutine that delays for 10 milliseconds, and we call it, let's say, twice, or we do the same. For example, here, instead of this, we just write call subroutine that delays for 10 milliseconds. Which is better? In other words, is it better to generate the delay using software or using the hardware? And I talked about this last time. Anyone has an idea? What if I replace this instruction with a call instruction that calls a subroutine that delays for 10 milliseconds? It will have the same effect. I will see a periodic square wave on pin 0 from port B. But is that approach better than what we have on the slide? Of course not. We said that there is a disadvantage for the software generated delays, which is basically if an interrupt occurs, an interrupt from any source occurs while the delay subroutine is being executed. Okay, assuming that interrupts are enabled while the delay subroutine is invoked, then what will happen? The delay subroutine will be interrupted, and the CPU will waste some time servicing the interrupt. Then once it finishes servicing the interrupt, it will go back to the delay subroutine and continue that delay. So in total, the effective delay that we will have in that case will be larger than the required delay. For example, if it is 10 milliseconds, and an interrupt occurs, depends on the complexity of the interrupt service routine and the tasks that are performed by the interrupt service routines. So the delay might get, let's say, 12 milliseconds, maybe 100 milliseconds. I don't know. Depends on how long does the interrupt service routine takes. So is this case applicable when it comes to using the hardware timer? Of course not, because the hardware timer is a separate hardware that is running concurrently in parallel with the CPU. So what is interrupted basically, if there is an interrupt while the delay is being generated by the timer, the hardware timer. If there is an interrupt, it is the CPU that is interrupted. It is not the hardware timer. So the hardware timer is still running and counting, and the CPU will service the interrupt. So this is the major advantage, one major advantage of using hardware generated interrupts, is the fact that they are more accurate in case interrupts are enabled in the system. In addition to the fact that using hardware timers release the CPU resources, leaves the CPU resources to other tasks so that we can have better efficiency. But this comes at the expense of course, additional hardware and additional cost that we need to add to our to the microcontroller. Okay, so this is about the timer. Any question? Try, as an exercise, try to write the C program that is equivalent to this. You write a C program to generate a periodic square wave of 50 with 50 hertz frequency on pin 0 from port B.
دكتور.
Yes.
طب يعني فور اكزامبل لو صار في انتربت بدس سب روتين، هلا التايمر بضل شغال بس اذا كانت تطقل بين 0 من بورت بي.
لا هلا اذا كانت يعني الفكره هون اذا كان يعني اذا كان الانتربت سيرفيس روتين طوله اقل من طول الاوفرفلو تبع التايمر، at the end رح ارجع على هاي الانستركشن واشيك على الفلاج. لكن اذا كان الانتربت سيرفيس روتين التايم اللي بياخده اطول من التايم تبع الاوفرفلو تايم تبع التايمر 0 yes I will miss this but when I finish the interrupt service routine I will come to this point مظبوط وراح
Yes.
الاقي انه الفلاج ست وراح اسوي توجل بس راح يكون مر وقت اطول من الوقت اللي هو 10 ملي سكند
يس تمام.
اوكي يعني في المشكله موجوده بس يعني it depends على التايم تبع التايمر 0 تبع التي سي ان تي تايمر.
تمام.
Okay. طيب let's move and look at some of the additional timing features that are that come inside this TIM module, this timer module. The first timing functionality that is basically uses the 16-bit free running timer is the input capture function. The input capture function. And the idea here, as I discussed last time, is basically in some applications, you want to record the time of some event. You want to record the time of some external event that is happening outside the microcontroller. And this event is basically an electrical signal which is binary. So what types of events that can be monitored in this case? Basically a falling edge or a rising edge, a transition from one state to another. So an event that is represented as a falling edge or as a rising edge can be used to record, might be required to record the occurrence, the time of occurrence for this event. We want to record the time at which this event occurred, which is basically represented as a falling edge or a rising edge. For example, we might, this falling edge might be coming from a switch, might be coming from a sensor, might be coming from another system. So we want to record that time for certain purpose. So in order to do that, this operation is basically called input capture. We want to capture the time for some input, And in order to do that, we need the following. We need a time base. So in our case, it is the 16-bit timer that we have just discussed. We need some hardware to monitor this event and to decide, to detect whether this event has occurred or not. So there is an input pin with edge detection logic that is associated with this functionality that monitors the input or the event under consideration and decide whether it has occurred or not. And once this event occurs, we want basically to record the time of that event. And the clock or the watch that we have is basically the TCNT counter or the free running counter. So we want to take the current time and record it and capture it. So we need a place to store the recorded value. So basically there is a capture register, 16-bit capture register, which is used to store the captured time at which the event occurred. So basically there are capture registers that come with the input capture functions. If you remember the block diagram, we have 8 input capture functions. So we have 8 time capture registers, TC registers from 0 to 7. So there are 8 input capture pins or channels. And there are 8 capture registers. If these input channels are used, or if these channels are used for input capture operations, then basically these registers are used to capture the time of the event when it occurs. Okay, and of course, this functionality is associated with interrupt service, such that when if the channel is enabled and it is used to capture the time of the event, when this thing happens, this can be used to interrupt the microcontroller. Then it can be used to interrupt the CPU. Okay, So basically, as we said, we can capture the time at the rising edge or at the falling edge. So this is kind of a configuration that we can apply to the input capture channel. We can configure them to capture the time at the rising edge or at the falling edge, or on both, on a rising edge or on a falling edge. So let's go into the details. In order to configure the type of the event that is to be captured, we can do that using this register, the TIOS register, the timer input output compare select register, TIOS register. So basically we have, as we said, we have 8 channels. Let me go back to the block diagram to remind you. So this is the block diagram. So these are the channels, which are basically the pins from port T. If you remember, this is pin 0 from port T, pin 1, pin 2, and so on. So these pins can be used for either input capture that we are discussing, or for the output capture that we probably discuss next time. So these pins can be used to monitor some event that is happening outside. And once a falling edge or a rising edge occurs here, we can take the time that is the current time from the free running counter and store it in the counter capture register, in the channel capture register, in the corresponding capture register. So this is basically the idea of the input capture. So in order to configure these channels as input, we need to go to this register, and this register basically decides whether the channel is an input capture or an output compare. I'm sorry, I said it is the edge. No, the edge is something, is another register. So this register basically is used to decide whether the channel is an input capture channel or an output compare channel. In our case, we are, for the time being, we are working with input capture, which is the default value on reset. This is the default value. So by default, these channels are are configured as input capture channel. Okay. Okay. Now, in order to configure what event forces the module to capture the time, basically we have the timer control register number 3 and 4, TSCR number 3 and timer control number 3 and timer control number 4. So basically here, as we said, we have 8 channels. We have 80 channels. So there are 2 bits for each channel. This is for channel 7. This is for channel 6. This is for channel 5, and so on. So here we have edge 7, edge 7A, edge 7B, edge 6B, edge 6A, edge 5B, edge 5A. So 2 bits basically are associated to each channel, and the value in each of these pairs basically specifies what type of event triggers the capture operation. So if these 2 bits are 0, 0, then the input capture is basically disabled. So nothing happens when the event occurs. 0, 1 capture on rising edge, 1, 0 capture on falling edge, and 1, 1 capture on both edges. So when the rising edge occurs, for example, there will be a capture. When a falling edge occurs, the module will also capture the time as well. Okay, so basically this register, the TIOS register, decides whether the channel is input capture or output compare. And these 2 registers contain 16 bits. Each pair of these 16 bits basically specifies what happens, what event triggers the capture operation, whether it is a rising edge, falling edge, or both. Okay, now, as we said, these input capture functions are associated with interrupt service. So whenever the event occurs, and the time is captured, this event can interrupt the microcontroller. That's why we have an interrupt flag for each of these channels. So this is interrupt, this is interrupt enable. We have interrupt enable bits for each of these inputs, for each of these channels. So this is timer interrupt enable register, TIE register. So basically here where we enable the interrupt, and in the TFLG register number 1, which is the timer flag register number 1, basically we have the flag. So this is the flag for channel number 7, flag for channel number 6, 5, and so on. Okay. So these are basically the registers that are related to the input capture, of course, in addition to the registers related to the timer operation, because the input capture functions, they use the timer as the time reference or the time base. So whenever you use the input capture functions, you will always need to configure the timer module in order to achieve certain timing to be used with the input capture. Now here, how to clear the timer, the flags. We know how to do that for the free running timer. We basically write one to the timer flag bit. The same case for the input capture flags or for the channel flags, because these channel flags are not only used with the input capture, these flags, these are the same for output compare. So if you look here, these input capture, output compare, interrupt flags. So these flags are the same for the input and the output, for the input capture and the output compare. That's why you can't enable both functionality for any channel at the same time. You cannot have any channel to be input and output, input capture and output compare at the same time, because some of the resources are common, some of the resources are shared. At least the pin, it is only one pin that is shared between two functions, output compare and input capture. So either the pin is configured for input capture or for output compare. The same thing for the flags. If the pin is configured for input capture, then the corresponding flag is associated with input capture operation and so on. Okay. So how to clear the flags? Basically, we can clear any of these flags by writing one to it, which is something we already know, or we can enable the fast flag clear mode, which is a bit in the timer control, the timer system control register number 1. We did not talk about it, but we saw it earlier. So what is meant here by this operation, which is very similar, if you remember, to what we have when we discussed the A to D, we had a fast clear mode for the A to D flags, right? So what is this mode? Basically, the flag or the corresponding, any of these flags is cleared if you read the capture register of the corresponding channel. So in this mode, a read from an input capture or write to the output compare channel causes the corresponding flag to clear, which is CNF, which is here. CNF, N is from 0 to 7. So this is useful actually, because if the event that let's say you are talking about input capture and the event occurs, so the time is captured and it is stored in the TC, in the corresponding capture register, TC register. So assume that you want to read this value in your program, and at the same time you want to clear the flag. So instead of writing two instructions to clear the flag and to read the register, you just read the register, and in effect this will force the flag to clear. So that's why it's called fast mode. You don't have to clear the flag, then you read the register, the capture register. You basically read the capture register, and in effect the flag will be cleared, and you will have the value inside the CPU once you read the register. So this is the basic idea. What we have here is basically how do we clear the flag. For example, to clear channel 0 flag, we basically write 01 to the flag 1 register, and it will be cleared. Okay, any question? So let's look at some of the applications where we might need to use the input capture functionality. On this, yes, يزن.
دكتور كنت بدي اسال هلا هو بس في تايمر واحد لل 8 انبوت كابتشرز.
Yes.
طب يعني كيف هذا يعني اذا كان في اكثر من انبوت كابتشر موجودين، يعني كيف بصير الفانكشن تبع هذا؟
هي ما في مشكله يا زلمه، انت عندك ساعه واحده بس عم بتراقب اكثر من ايفنت، واللي بدك اياه بدك تسجل الوقت تبع كل ايفنت من هدول. يعني تخيل انت معك ساعه وعم بتراقب المتسابقين as they pass through the finish line. اوكي.
Yes.
فانت بتيجي تحكي الساعه شغاله، ما في داعي اجيب ساعه لكل واحد منهم، انا بجيب ساعه واحده وبس يمر اول واحد بحكي مر الساعه واحده، الثاني مر الساعه 1:05، الثالث مر الساعه 1:10 and so on.
اوكي يس تمام.
يعني انا ما بدي تايمر لكل واحد من الانبوت تشانلز، انبوت كابتشر تشانلز، انا بدي ساعه واحده ووظيفه هي الساعه تسجل الزمن بس.
اوكي، يعني هي يعني just recording the time، الريفرنس تبعها بكون جاي من
يس، انا ما بدي 8 ساعات، انا بدي ساعه واحده احملها بايدي وبسجل التايم لعدد لا نهائي، خلينا نفترض ثيوريتيكلي من الايفنتس. مظبوط؟
يس.
اوكي
تمام.
تمام. Okay, so what applications can benefit from the input capture functions that is available in the TIM module? Basically, for example, here we have event arrival time. So basically, you want to record, all what you want to do is to record the time of that event. Your application might be recording or period measurements. You want to measure the period of some periodic square wave. So in order to measure the period, basically you need to store, for example, to monitor this rising edge, record its time, then you wait for this rising edge and record its time, then you take the difference in time, and in this case you have the period, so you can measure the period. For example, your application might be measuring the pulse width of some input or some signal, or basically measure the duration of some event. This is the duration of some event. For example, somebody pressed a button, and when he pressed the button, this forced the input to be high, so there was a rising edge, and then he pressed the button, kept pressing the button until this moment where he released the button. So you want to record the time of that event, the duration of that event. So you want to record the time of this rising edge, the time of this falling edge, you subtract, then you have the pulse width or the duration of that event that you are monitoring. One simple application basically is interrupt generation. Let's forget about time. We don't care about time. And we basically want to interrupt the microcontroller when there is a falling edge on one of these pins, or there is a rising edge. We already had such functionality when we talked about what? IRQ interrupt, right? In IRQ, we can interrupt the microcontroller based on some event that is coming from outside. However, this is only one pin. What if we want to monitor more than one event to interrupt the microcontroller regardless of the time? We can use these channels as an input to interrupt the microcontroller when there is a falling edge, when there is a rising edge, when there is both rising or falling edge, regardless of their time. So we can enable any of these channels to interrupt the microcontroller, and we don't care about time. And there are many applications, for example, event counting during some period of time. So for example, when the first event occurs, you record the time, and Then you say, I want when the time reaches certain value, I want to record how many times the event occurred. And in this case, you need a counter in your program, a software counter, to count how many events occurred during this period of time. And there are many other applications like the time reference, which is used in conjunction with output compare, with which we will cover later. Duty cycle measurement, which is basically you measure the pulse, this pulse width, it is basically period measurement and pulse width measurement. You measure the duration of this pulse, then you measure the period, and then you compute the duty cycle, which is basically the on time divided by the period. This is the definition of the duty cycle. Your application might be phase difference measurement. You want to measure the difference between the phase difference between two periodic signals. Let's say this is fed to one of the input capture channels. This is connected to another input capture channel. So basically, you capture the time of the first rising edge, you capture the time of the first rising edge here, you subtract, you have the difference, the time difference between the two signals, and basically you can convert it to phase by basically this, using this simple formula, and probably you know this. Okay, so these are some of the applications that can take advantage of the input capture functionality. Okay, so let's look at an example which is about period measurement. We want to measure the period. We want to use we want to use the input capture channel. Oops, why it's doing this? We want to use the input capture channel 0 to measure the period of some signal, which is unknown. Now, all what we know about this signal, that the period is to be shorter than 128 milliseconds. It is less than 128 milliseconds. We need to know something about the period because we need to configure the timer properly. So assume now that the E clock is 24 megahertz. And what is required here, your program is to report the period as the number of clock cycles. In other words, you don't have to convert it to time. You don't have to convert it to time by multiplying it by the E period in order to get the time. Just how many cycles have elapsed in the counter. So we represent it as number of cycles. So how to do that? We want to measure the period. What should we do? We need to configure the timer. We need to configure the input capture channel number 0. Now, what can we do for input capture channel number 0? Basically, we need to configure it, for example, to capture 2 consecutive rising edges or 2 consecutive falling edges. So we record the time of the first edge, we record the time of the second edge, and basically now the time that we record that is captured is basically the number that is available in the counter register. This number has to be multiplied by the E period in order to get the time in seconds. Okay. So for the input capture channel, it is straightforward. We need to configure it to capture 2 consecutive edges of the same type, either rising edges or falling edges. What about the timer, the free running timer, which is our time base? Now here we need to look at here. Now our timer is basically a 16-bit timer. And given that E clock is 24 megahertz, then the longest time that we can measure, given that the prescaler is 1, is basically 2 to the power 16 divided by 24 megahertz multiplied by prescaler of 1, which is 2.73 milliseconds. So if we don't want to play with the prescaler, the longest time that we need to measure is 2.73 milliseconds. While the period of the incoming signal might be as long as 128 milliseconds. So what can we do? What is the problem here? The problem here is that let's assume that we just started the counter, the timer, we enabled the input capture, and the first rising edge arrived at time equals 0. Now what will happen after 2.7 milliseconds? The timer will overflow, and let's assume that by that time we have not received the second rising edge on the channel. So what will happen? The timer will overflow, but we have not. So it will restart and will start counting from 0. So the second rising edge has not arrived. So how can we overcome this problem? How can we record the time of the second rising edge? Basically, we have two approaches. Either we try to extend this time, which is 2.73 milliseconds, to make it larger or very close to 120 milliseconds. Or the other approach is basically to have a counter in our program to count how many times did the timer overflow before the second edge arrived. So for example, let's say that our signal has a period of let's say 6 milliseconds. The period is 6 milliseconds. Then in this case, our timer will overflow after 2.73 milliseconds and after 5.4 milliseconds, right? So we have two overflow occasions, and then it will count some value before the second edge arrives at 6 milliseconds. Okay, let me do this. So our timer basically overflows every 2.73 milliseconds. Every 2.73 milliseconds. However, the first hour, let's assume that our periodic signal has a period greater than 2.73. If it is maximum 2 milliseconds, then we are fine. There is no problem. But if it is greater than this, there is a problem. Let's assume that our rising edge, first rising edge arrived here at 0.5 millisecond. What is this? Yeah, 0.5 milliseconds. If the second rising edge arrived here, there is no problem. We record this time. Let's say this is 1.5. So we say 1.5 minus 0.5, it is 1 millisecond. So the period involves 1 millisecond. So this is very optimistic. This is very optimistic because we assume that we receive the first edge here, okay, and the second edge here. However, what if the period is larger so that the second rising edge arrived here? At this time, the timer will overflow, so it will really start counting from 0 up to 2.73, right? So what is the total time? The total time basically is this minus this, but this time will not, let's say it could be 0.3 millisecond, okay? So in this case, we need to know how many times the counter has overflown, okay, in order to measure the period, okay? Now, instead of having a counter, what he did here, basically, he tried to extend the overflow period to the closest value to 128. So he chose the Prescaler of 64. 64 times 2.73, it should be something what? Like around 170 milliseconds, 0. So what will happen here is if you receive the edge here and the edge here, you don't have to count how many times the counter has overflow. all what you need to do is to subtract this minus this. You will tell me this time might be less than this. For example, this might be 0.3, this might be 0.5. So the time will be minus 0.2. But technically, we are not subtracting like this when it comes to subtracting binary. Because we are talking about 16-bit timer, it is modulo subtraction. So this is in binary, it has some value. Let's say 1011. This in binary 00000, 16 bits. This is 0001111, for example, whatever. So when you subtract, basically it is modulo subtraction. So basically, you know what is modulo. You are moving on a circle. So this is your counter. It is counting like this, of course, and it comes back to the same value. It doesn't go to infinity. So when you, for example, suppose this is your recorded time for the first edge, and this is the recorded time for second edge. This is T1, this is T2. When you perform subtraction in binary, it is modulo subtraction. So when you subtract T2 minus T1 and the subtraction is modular subtraction. Basically, you will count how many increments you needed to reach here. So this is what is meant by modulo subtraction. So T2 is less than T1, so the time will be negative, but this is true for the usual subtraction. For modulo subtraction, no, you are taking this. So if you increase the overflow time to up to 170, the next overflow will be at 340, okay? So even if your first edge arrived here, your next edge will be somewhere here. So one subtraction will do the job. However, here, if we keep it like this, the second edge might arrive here, for example, after one overflow, two overflows, three overflows. So we need to count how many overflows. Then we add the difference between this and this, between T2 and T1. Okay, so if there is only one overflow incident, then we can just do the modulo binary subtraction to get the answer. However, if there is multiple overflows, then we need to keep track of how many times the timer overflowed. And this is more practical in case we don't know any information about the maximum period length, So there are two choices. Either we choose a prescaler such that only one overflow may occur in our calculations, or basically we take any value for the prescaler, for example, leave it 1, and just use a counter in our program to count how many times the counter overflow. And the period basically will be T2 minus T1 plus how many times did the counter overflow multiplied by the overflow time, There is an example later that details this, but in this example, we will stick to this approach, which is setting the prescaler to 64 for the timer, and basically subtracting T2 minus T1. So this is the flow chart for the program. Basically, choose capture on rising edge, select the timer prescaler to 64, not 16. This is wrong. It should be 64. Clear the flag for the input capture channel number 0. Wait for the flag to be set, which means we have received the first edge. Now, automatically, the time in the timer will be latched or captured and stored in the in the corresponding capture register, we will need to clear the flag in order to wait for another incident of that event. So we will wait for the flag again to be set, which means that we have received the second edge. Then we basically take the difference. So we need to store the first captured value, then we subtract the timer capture register for channel 0 minus the recorded value here. We get how many cycles. This is very important. It's not time in second. How many cycles has elapsed between the first edge and the second edge. So this is the program in assembly and C. Here we have two variables, edge 1 and period. Edge 1 is basically used to store the time of the first edge. And this variable or memory location is basically used to store the period that we calculate at the end. So what is done here, basically enable timer counter and enable fast timer clear. So basically we store this value in the control register for the timer system, control register number 1 for timer system, enable the timer and the fast clear flag, enable input capture on channel 0 by writing bit clear TIOS in this register IOS 0. What is IOS 0? Basically, it is a value that is defined as an equate statement in the include file. And basically, it should be what? If you, this is kind of a mask. What it is the value? 0, 0, 0, 0, 0, 0. It is all zeros. If you go to this register, in order to enable the input capture on channel 0, you need to store a 0 in bit number 0. So if you look at the include file, this label or this value basically is zeros. So it is just only to make it easier for you to work with names. So this is IOS 0. So enable input capture 0. Then disable timer overflow interrupt, set the prescaler to 64. We know how to do that by going to this register. Enable capture on rising edge on channel 0 by going to this register and writing this value. You can go back to this register and figure out how come it is 0. It is 0, 1. You clear the flag by writing 1 to it. And this is basically a value that is defined in the include file, hash C0F. So you write C0F. So this is not a hexadecimal value. This is a label that is defined in the equate statement, which is basically TFLG1 to clear C0 flag. So basically this value is all zeros but 1. The least significant bit is 1 because the location of the 0 flag, C0 flag, is the least significant bit. You wait for the flag to be set, so you pull the flag. We are not using interrupts. Once the flag is set, you take a copy of the timer capture 0 register and store it in the edge 1 to store the time in cycles for the first edge. Then again, you wait for the second flag, you read the value into accumulator D, then you subtract edge 1 from this value and you store it in period. Now the value that is stored in this location is basically the number of cycles that have elapsed between edge 1 and edge 2, okay? And as we said, these two edges might fall within the same window of operation for timer for the timer before it overflow, or in two different windows. But even though when you subtract, in this case, it is modular subtraction. So you basically count how many jumps you need to reach if you go from T1 to T2. Okay? This is the code in C. And the idea of modular here is overcome by defining the variables as unsigned. Defining the variables as unsigned. So try to match what we did in assembly to what we did here. So of course, doing that in C is much easier. All what you need to do is to figure out what values to be stored in the corresponding registers. And the same thing here for the flags. For example, this is a constant that is defined in the include file or the header file and so on. Okay. Okay. So the other, I know that the time is over, so I will leave you with this example. It is how to use the pulse, the input capture for pulse width measurement. If you have time, look at it. I will not talk about it, but it gives you a better idea on what I did on the board, on what is the difference, how to determine the difference in time, given the fact that the timer overflows or resets. When it reaches the maximum, it resets. So here it uses the second approach where we count how many times the timer overflow in order to determine the pulse width. So look at it, and I will go over it very quickly next time. Okay, so okay, so next time we'll look at this example and we will cover the last thing, which is the output compare functionality. Okay, any question?
دكتور الله يعطيك العافية.
الله يعافيك.
بس كنت بدي أسألك عن موضوع إنه كم بنحسب الأوفر فلو في اللاست إكزامبل. يعني هذا اوتوماتيكلي مثلا إحنا ما بنقدر نعمل له، ما بنقدر نشوف، بس إحنا نكتب له بروجرام. يعني مثلا صار عندي اوفر فلو أول مرة، بعدين صار عندي ثاني مرة، لما أجي أعمل السبتراكشن ولا اوتوماتيكلي بيصير؟
لا ما بصير automatically. That's why and I said you need to define a counter in your program. Whenever you detect an overflow, you increment the counter. As long as you have not received the second edge, you keep incrementing that software counter whenever the timer overflows. Once you receive the second edge, you take the value, the number of overflow incidents, you multiply it by the timer overflow time or the cycle time. Okay. So you get what? You get how many times the timer in seconds. Then you add T2 minus T1.
تمام.
Okay. Think about it, straightforward.
Okay.
And this is illustrated in the period in the pulse width measurement example. It is used in example 8.3. All right. الله يعافيك يا رب. تمام. إذا نراكم يوم الأربعاء إن شاء الله. Hopefully it should be the last lecture in terms of the material to be covered. Okay, and for homework 3, I will make sure that Muhammad يعني try to be flexible شوي. يعني بدناش يكون شديد عليكم شوي.
الله يعطيك العافية دكتور.
الله يعافيك يا رب. تمام. يلا سلام عليكم.